Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator, the number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers and their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean. Hey guys, welcome to this Symmetrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say 1/8 instead of 8, or 1/3 instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8. So our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5. An improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3/8 is a proper fraction, 8/3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9/9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3/4. We also have equivalent fractions. Equivalent fractions are 2 different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If 2 fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8, and that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common, such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
You may have heard a math teacher or two say math is a language. If that is true, then algebraic rules and notation should be considered the grammar and punctuation of the language of math. Some students who struggle with math are confused by how to apply the rules and interpret the notation. In this video, we will focus on the notation and interpretation of exponents. This video will focus on the meaning of exponents that are natural numbers, also referred to as counting numbers, which are 1, 2, 3, things like that. Other types of exponents are interpreted differently and will be covered in other videos. Let's start by quickly reviewing some terminology. An exponent is written as a superscript on a number or algebraic expression, which is referred to as the base. There are a few ways to verbalize a power. This simple example can be read as 5 squared, 5 to the second, 5 raised to the second power, or 5 raised to the power of 2. In any case, the exponent should be interpreted as repeated multiplication. Whatever is defined as the base should be multiplied by itself however many times the exponent implies. For example, 5 squared equals 5 times 5. This can then easily be evaluated as 25. Let's look at some more examples. 7 cubed. This time the base is 7 and the exponent is 3. This can be read as 7 to the third or 7 cubed. Raising a base of 7 to the power of 3 means to multiply 7 by itself 3 times. 7 times itself 3 times equals 343. Let's try another one, but this one will look a little different. -2 squared. It is important to point out that parentheses are being used with this example to define the base. -2 is being raised to the second power. The interpretation is the same. Simply multiply -2 by itself twice. Multiplying two negative numbers using parentheses results in a positive value. But if we were to take the parentheses away and instead say -2 squared, then our answer would be -4. Why? Because the 2 is squared before the effects of the negative can take place. So we have 2 times 2 equals 4, and then the negative affects it. Let's try another one with negatives. -5 cubed. This is equal to -5 times -5 times -5, which gives you -125. Powers of 10 are used frequently in math and science applications. Scientific notation uses powers of 10 to express very large or small values in an efficient and organized manner, but we'll dive into that topic in another video. Exponents are also used to raise algebraic expressions to powers, but the meaning is the same. Multiply whatever the base is by itself, however many times that is indicated by the exponent. Here are a few examples. X cubed is equal to x times x times x. As you can see, the notation x cubed is a more efficient way to write the expanded version of x times x times x. 2x cubed is equal to 2 times x times x times x. Notice that the base here is x. Adding parentheses to an expression changes the meaning. If you put in parentheses, 2x cubed means 2x times 2x times 2x, which is equal to 2 times 2 times 2 times x times x times x, which when you simplify that, gives you 8x cubed. Let's try one more example before we go. X plus 2 squared. Once again, the parentheses here are used to define the base to be x plus 2. The exponent of 2 instructs you to multiply this base by itself twice. So it equals x plus 2 times x plus 2. Multiplying these two binomial expressions results in the quadratic expression x squared plus 4x plus 4. So, as long as you can identify the base, the multiplication of that base by itself becomes pretty straightforward. As mentioned, the interpretation of notation in math is half the battle. Practicing the basics is key in order to gain confidence for more complicated math content. Hello, and welcome to this video about proportions. In this video, we will explore what proportions are and what it means for quantities to be proportional, and mathematical and authentic applications of proportions. Before we get into proportions, we need to quickly review ratios. Recall that a ratio shows the relative sizes of two or more quantities. For example, in the alphabet, the ratio of vowels to consonants is 5/21. In a standard deck of cards, the ratio of face cards
to total cards is 12/52.
In all circles, the ratio of the circumference to the diameter is pi. There are many ways to represent ratios. Here, we'll mainly be working with the fractional representation. Ratios are not exactly fractions, but they can behave just like them. Now on to proportions. A proportion states that two ratios are equal. If I want to cook 1 cup of white rice, I would combine it with 2 cups of water. In other words, for every cup of rice, I need 2 cups of water. So the ratio of rice to water is 1/2. If I wanted to double the recipe, I would need 2 cups of rice and 4 cups of water. So 1 over 2 is equal to 2 over 4. These recipes are proportional because this is a true statement. In other words, their fractional forms are equivalent. On the other hand, the recipe for brown rice calls for every 1 cup of rice, 3 cups of water. The recipes for white rice and brown rice are not proportional because 1 over 2 does not equal 1 over 3. Let's look at using proportions to find quantities. In a standard deck of cards, the ratio of face cards
to total cards is 12 over 52.
Dealers in casinos often use 8 decks for blackjack. How many face cards would they use? In 8 decks,
the ratio of face cards to total cards is still 12 over 52.
So these quantities of cards are proportional. There would be 96 face cards. Let's look at another example. The length of a rectangle is 4 units, and its width is 3 units. The length of a second rectangle is 8 units, and its width is 3 units. Are the rectangles proportional? Let's write this out. 3 over 4 does not equal 3 over 8. Since the ratios of length to the width are not equivalent, the rectangles are not proportional. Now suppose you're driving a car at 75 miles per hour, heading to a destination that's 300 miles away. That is, for every hour that passes, you drive 75 miles. In this case, distance is directly proportional to hours, because as hours increase, distance also increases, and the rate of increase does not change. This table shows an increase of 75 miles for every 1 hour. The graph shows a straight line intersecting the origin. The equation is of the form y equals kx, where k is the constant of proportionality. Here, the constant of proportionality is 75. Every hour amount is multiplied by 75 to calculate distance. Now let's consider the same journey but with a different relationship. You travel the same 300 miles, but instead of traveling at 75 miles per hour, you travel at 60 miles per hour. How much longer does the trip take at the slower speed? From the previous example, we know that y equals 75 miles per hour times by 4 hours equals 300. Now you are driving slower. So you have y equals 60 times x, which represents the number of hours traveled, equals 300. So to solve for x, you divide by 60 on both sides and get x equals 5. Here, distance is inversely proportional to time because as time increases, distance to the destination decreases. You get closer every hour. The distance doesn't change, so the constant of proportionality is 300. What does change is the speed. The graph shows all possible speed-time combinations to drive the 300-mile distance. If you drive 300 miles per hour, it would take you 1 hour. Whereas if you drive 1 mile an hour, it would take you 300 hours. Equations showing inverse proportionality have the form y equals k over x, where k is, again, the constant of proportionality. Here, the distance 300 could be divided by the number of hours to calculate the speed, or it could be divided by the speed to calculate the number of hours. Suppose you drove to the same place again, and it took you 3.5 hours. How fast did you drive? Well, you've got y, which is your speed, is equal to k, your constant of proportionality, which is 300, divided by the total number of hours, 3.5, and that gives you that your speed is roughly 86 miles per hour. Now that we've covered proportions, let's talk about percentages. When we deal with percents, they can be treated like proportions. The word percent literally means per 100. So knowing that, we can figure out any relationship we need to. The key to percents is figuring out the whole and the part. Simply put, the whole is the quantity represented by 100%, and the part is the piece of the whole represented by some other percent. Generally, proportions with percents look like this. The whole amount over 100 is equal to the partial amount over the partial percent. Your restaurant bill comes to $33.75. You received exceptional service, so you want to leave a 20% tip. How much do you tip? Using a bar model can come in handy when visualizing these problems. For instance, $33.75 over 100 is equal to whatever your tip is going to be over 20. So if you look, we can do 33.75 over 100 divide it by 5 over 5, and that gives you 6.75 over 20. Since the total amount is proportional to the tip amount, we can simply divide the total amount by 5 to arrive at the tip amount. Division by 5 also makes sense because 20 is 1/5 of 100. Suppose you went back to the restaurant and had a bill of $26.34, but decided to leave the typical 15% tip. How much do you leave? The bar model still helps us visualize. So we have 26.34 over 100 is equal to our tip amount over 15. This time, it's not as easy as dividing by 5, since 15 doesn't go evenly into 100. Here's a different way of using equations to think about it. If 26.34 is equal to 100%, then 0.2634 is equal to 1%. From there, we're going to multiply both sides by 15, and you get 3.941 is equal to 15%. Now we know you left about $3.95. You visit a store that's having a 25% off sale. You pick out some clothes and your total comes to $140.67. How much would full price have been, and how much did you save? With a 25% discount, that means you paid 75% of the full price. So you have your original price over 100, which is equal to 140.67 over 75. If 140.67 is equal to 75%, so if you divide both sides by 3, you get 46.89 is equal to 25%. And then if you multiply both sides by 4, you get 187.56 equals 100%. The original price was $187.56, so you saved $46.89. Suppose your friend went shopping with you and used a coupon for an extra 10% off. This coupon was calculated after the total was calculated, so it came off the sale price. What was the total discount percentage from the original price if your friend spent $211.89? So if you have $211.89 is equal to 90%, then if you divide both sides by 9, you get 23.54 is equal to 10%. From here, you would multiply both sides by 10 and get 235.4 equals 100%. So 100% of the sale price equals 75% of the original price. So we have $235.40 is equal to 75% of the original price. From here, if you divide each side by 3, you'll get $78.47 is equal to 25%. Then we'll multiply both sides by 4 to get $313.87 is equal to 100%. We can figure out a percentage by simply dividing the part by the whole and then multiplying by 100. In this case, the percentage paid is the amount paid over the original price times 100. So from the previous example, we have this. This is the percentage your friend paid. 100 minus 67.5 is equal to 32.5%, which is the total discount percentage your friend saved. Hello, and welcome to this video about expected value. In this video, we will explore what expected value is and how it can be used. Expected value is an application of probability that is typically used to help people make decisions about the viability of risks, most often financial risks. The big idea is to multiply the probability of each potential outcome of an event by the value of that outcome and add all the results together in order to make a more informed decision. Let's begin by talking about coins. The probability of flipping a coin and it landing on heads is 1/2, as is the probability of landing on tails. Let's say that you are thinking about playing a game that costs $1 to enter. The game will pay you $2 if the coin lands on heads and $0 if the coin lands on tails. Let's make a table. Here we have heads and tails, and on the left we have the value of the outcome and the probability of the outcome. If you win the game, you get $2. But since you pay $1 to play in the first place, we subtract that from the $2, which gives us $1. This means that if the coin lands on heads, you are $1 richer than before you played. Now, if the coin lands on tails, you win no money, and we still have to subtract that $1 we spent to play the game. So we come away with $1 less than we started out with. And like we mentioned before, a coin has two sides, so the probability of the outcome in both cases is 1/2. To calculate the expected value, we'll use this formula. The expected value of x equals the probability of outcome 1 times the value of outcome 1 plus the probability of outcome 2 times the value of outcome 2. If we plug in our numbers, our calculation looks like this. An expected value of $0 illustrates that the probabilities of the event outcomes and the values of those outcomes are equal, as shown in the table. The game is balanced. You decide not to try the coin game another time and instead head over to the movie theater. On the concession counter is a drawing that costs $1 to enter. The first entry drawn wins 2 movie tickets, a $30 value. The second entry drawn wins a large popcorn and a drink, a $15 value. And the third ticket drawn wins a large popcorn, an $8 value. You ask the manager how many entries they tend to get for drawings, and he says about 100. Do you take the chance? Let's fill in our table looking at each prize individually. You know that the drawings are stacked against you in the first place, but since the expected value shows a loss that is less than half of your cost to enter, the risk is acceptable. You decide to take the plunge. After the movie, you head home. You check your mail and find an ad for bundling TV, phone, and internet in one package using a service that isn't even available in your area. The ad is elaborate, high quality, and beautifully printed on glossy cardstock. You wonder how the company makes any money sending these costly ads to places that can't even take advantage of them. The company knows that they'll get about a 1% return on their mail investment. In other words, they'll get one long-term customer for every 100 ads that are sent. If a long-term customer is worth at least $3,600 and each ad costs $5 to print and mail, is sending direct mail a profitable idea for the company if they send 10,000 ads? On average, the company can expect to gain $31 for each ad that is sent, which is a very lucrative decision. You throw the ad in the trash and begin looking forward to the outdoor festival you are planning to attend the next day. You check to see what the weather will be like and discover a 75% chance of rain. You remember an article you read describing how $25,000 was spent by the city to put the festival together. Tickets cost $10 a piece, and the expected turnout is about 8,500 people. Is it still a good idea to put on the festival given the rain chances? Let's map it out and see. With these rain chances, the expected value of the city's investment is negative $3,750. They may want to postpone the festival for a sunnier day.
Hi and welcome to this video about polygons. In this video, we will explore 4 things. 1. What polygons are. 2. The different parts of a polygon. 3. Ways to classify polygons. And 4. How to determine the number of diagonals in a polygon. The term polygon is derived from the Greek words polis, meaning many, and gonia, meaning angle. So polygons have many angles. First, let's explore how polygons are constructed. Consider the geometric point, represented by a dot. The point is zero-dimensional. It has no length, width, height, nothing. Now let's consider 2 connected points. This is called a line, or a line segment. A line segment is one-dimensional. It has length, but no width or height. When multiple line segments are connected end to end, polygons such as this can be formed. Polygons are 2-dimensional. They have no thickness, like this. In order to be a polygon, the shape must be closed. In other words, every endpoint must be connected to another endpoint. This figure is comprised of connected segments, but the result is not a polygon. This shape is closed, but not made up of any connected segments, so it is also not a polygon. A polygon is defined as a 2-dimensional closed shape composed of line segments. The sides of polygons are called edges, and the angles created where the edges intersect are called vertices. Polygons also have as many edges as vertices. Polygons are named by the number of edges they have. This polygon has 3 edges, 3 vertices, and is called a triangle. The triangle has the smallest number of edges and vertices of any polygon. It is impossible to create a 2-sided polygon. Some common polygons are quadrilaterals, which have 4 sides, pentagons, which have 5 sides, hexagons, 6 sides, heptagons, 7 sides, octagons, 8 sides, nonagons, 9 sides, decagons, 10 sides, and dodecagons, which have 12 sides. Though polygons with any number of edges have names, the general n-gon is typically used for all other polygons, where n represents the number of sides. For instance, a 30-sided polygon is called a triacontagon, but it's often simply called a 30gon. Polygons can be regular or irregular. Regular polygons have congruent edges and congruent vertices. For example, this is a regular quadrilateral. The edges are the same length and the vertices have the same measure. This is an irregular quadrilateral. The vertices have the same measure, but the edges have different lengths. This is an irregular quadrilateral. The edges are the same length, but the vertices have different measures. This is an irregular quadrilateral. Neither the edges nor the vertices have the same measure. Polygons can also be convex or concave. When one or more vertices of a polygon measures more than 180 degrees, the result is a concave polygon. For example, this is a convex hexagon. All the vertices measure less than 180 degrees. This is a concave hexagon. One vertex measures more than 180 degrees. Now remember, only polygons with 4 or more sides can be concave because it's not possible for a triangle to contain an angle measuring more than 180 degrees, which is a straight line. Concave polygons cannot be regular because all the vertices will never be the same measure. Polygons also contain diagonals. Diagonals are line segments joining two vertices that are not next to each other. As you can see here, this irregular convex pentagon has 5 diagonals. This is an irregular concave pentagon. It also has 5 diagonals, even though the concavity causes diagonals to lie outside the polygon. Triangles do not have diagonals because there is no way to connect two vertices with segments that are not edges. Now that you know the basics of polygons, let's use the diagrams to figure out a formula for finding the number of diagonals in any polygon. In this case, the number of diagonals connecting to each vertex is 2, which is 3 less than the number of vertices, 5. 2 diagonals connect to each vertex. This is true of all diagonals of all polygons. A nonagon has 9 minus 3 equal to 6 diagonals connecting to each vertex. The number 3 is not arbitrary here. From any vertex, diagonals cannot connect to the vertex itself or to the vertices that they are 1 away from, because it would be edges. That makes 3 vertices from every vertex that aren't included. To generalize this, we'll use n minus 3, where n is the number of vertices of the polygon. Now each vertex has the same number of diagonals connecting to it, so in this case we can see that the total number of diagonal connections to vertices is 5 times 5 minus 3, which is equal to 10. In general, we can say the total number of diagonal connections is n times n minus 3. When we figure out this total, though, we are counting each diagonal twice because diagonals have 2 endpoints. In order to figure out the number of unique diagonals, we need to divide our total by 2. In our pentagon, this looks like 5, which corresponds to our diagram. Therefore, for any size polygon, our equation can be written as this: n times parentheses n minus 3 all over 2, or divided by 2. Conceptually, this can be remembered as Using our formula, we can determine the number of unique diagonals in, for example, a 17gon, which is equal to 119 unique diagonals. We can also see algebraically that triangles have no diagonals. We can also figure out how many edges or vertices a polygon has by the number of unique diagonals. Suppose a polygon has 44 unique diagonals. How many edges does the polygon have? Alright, so here we are at an answer. N, the number of edges the polygon has, is either equal to 11 or negative 8. Because what we want to do is we want to make sure that we end with the result of 0, which means that n somewhere has to be 11 or negative 8 in order to get us multiplying 0 by another answer, resulting in 0. Since n can't be negative, because we can't have negative edges, it can't be negative 8. So we know that our answer is 11. The number of edges is 11, making it an 11gon.
If you have ever created a website before, you know that underneath all the images, buttons, and menus are lines and lines of computer code. The coding is all textual in nature, meaning it consists of words, numbers, and phrases, but it results in the physical images, lines, boxes, and layouts that you see on the website. Similarly, the numbers, equations, and expressions you're familiar with from your experience with algebra can also be expressed in a visual format, such as in the form of lines and other shapes. How is this accomplished? That is exactly what we will explore today in this video about the Cartesian coordinate plane. René Descartes was a French philosopher who came up with a plane upon which numbers and equations could be graphed. Legend has it that while laying in bed, Descartes noticed a fly on the ceiling and developed his plane to indicate the fly's position. The plane consists of two perpendicular intersecting lines, one horizontal and the other vertical. The horizontal line is called the x-axis, and the vertical line is called the y-axis. The x-axis is used to designate the horizontal location of points on the plane, whereas the y-axis is used to designate the vertical location of points on the plane. The lines intersect at what is called the origin, right there, which has a value of 0. Let's take a closer look at the x-axis. We'll begin all the way on the left side and label it. -3, -2, -1. After the origin, which as we mentioned has a value of 0, we'll continue with 1, 2, and 3. This may look familiar to you as it resembles the traditional number line you may have used to solve math problems. We do the same thing with the y-axis, starting at the very bottom, -3, -2, and -1. Then we move above the origin and we do 1, 2, and 3. As you can see, points to the left of the origin have a negative x value, whereas the points to the right of the origin have a positive x value. Similarly, points below the origin have a negative y value, whereas points above the origin have a positive y value. Each point plotted on the plane has a set of coordinates written in the following manner: x, then y. Meaning for any given point, we write its location on the x-axis first, then it's followed by the location of the y-axis. You may have noticed that the plane with the intersection of the x-axis and y-axis has 4 squares. So right here. Each of these squares is called a quadrant. The top right is the first quadrant. The top left is the second quadrant. The bottom left is the third quadrant. And the bottom right is the fourth quadrant. As you can see, the quadrants are typically labeled using Roman numerals. To bring it all together, let's look at some examples. Say you were given the coordinates of 1, -2. Our first step would be to find 1 on the x-axis, then go down to -2 on the y-axis. Then we mark our point of 1, -2. Let's try another. Say you wanted to find, say, -3 and 2. First, we find -3 on the x-axis, which is right here, and then continue up to 2 on the y-axis. Right there. We mark our point. It's important to note that our first point is located on the 4th quadrant, whereas our second point is located in the 2nd quadrant. Let's take it a step further and graph a very simple equation. We'll need an expanded plane, so let's make one that goes from -5 to 5 on both the x and the y-axis. Say you wanted to graph y equals 2x plus 1. The first thing we'll do is draw a table with one column for x values and another column for our y values. We begin by plugging in values for x and seeing what the corresponding y value will be. Let's start with an x value of -3. So if we have -3, we essentially plug it into our equation here. So I'll do that down here. So y is equal to 3 plus 1. 2 times -3 is -6 plus 1. Y is equal to -5. So we plug in -5 here. This makes our first point -3, -5. Going to our plane, we first find -3 on the x-axis, then -5 on the y-axis. So going all the way down here, we'll plot our point. Now let's try an x value of -1. Once again, we write -1 in the x column. -1. So now we need to find our corresponding y value by plugging it into our equation. So we get 2 times -1 plus 1. So y is equal to -2 plus 1, which gives us y is equal to -1. So we put -1 right here. So now we have our next coordinate as -1, -1. So first we go to our x-axis, find -1, and go down to -1, and draw our mark. Let's quickly plot 2 more points. We'll try an x value of 1. So now we have our next set of coordinates. That's 1 and 3. So we go and we find 1 on the x-axis, then we go up to 3 on the y-axis. We'll finish off with an x value of 2. So we put 2 in our x column, and then plug it into our equation. All right, so that gives us our next set of coordinates, which is 2, 5. So we find 2 on our x-axis, and then go all the way up to 5 on our y-axis. Now that we have our 4 plotted points, we turn back the clock to the games we played before smartphones came along and connect the dots to form a line. The line ideally shows how we would graphically represent y equals 2x plus 1. It is a visual representation of the equation and brings our understanding of algebra and geometry to the next level.
Hello, and welcome to this video about line graphs. Today we'll explore what a line graph is and what type of data it's used to represent. We'll also learn how to use line graphs to interpret situations in the real world. Before we get started, let's review a few things. First, a graph is a diagram that shows the relationship between 2 quantities, which we call variables. These variables are measured along the x-axis and y-axis on a coordinate plane. A line graph is a type of graph that displays quantitative data as a series of points called markers, or data points. These data points are connected by straight line segments. The connected data points show the relationship between 2 variables. A line graph is typically used to show information that changes over time. Let's take a look at an example. This line graph shows the change in a company's profits over several years. The x-axis is labeled year and the y-axis is labeled profits. We see that line segments connect the data points plotted on the graph. Since the line segments are generally moving in a positive direction, we can say that the company's profits tended to increase from 2006 to 2013. Let's take a look at the line segment connecting the data points for the years 2009 and 2010. We can see that this particular line segment is positioned in a downward or negative direction. This tells us that the company's profits decreased from 2009 to 2010. What do you notice about the line segment connecting the data points for 2012 and 2013? They form a straight horizontal line. This shows that the company's profits neither increased nor decreased during this time frame. Instead, they stayed the same. When constructing a line graph on a coordinate plane, the x-axis is always used to plot the independent variable, and the y-axis is always used to plot the dependent variable. With line graphs, the independent variable is usually time. In the graph we just looked at, the independent variable is years, which is a measurement of time. The dependent variable is the factor that changes over time. In our example, the dependent variable is the company's profits, which increased and decreased from 2006 to 2013. Line graphs are an important part of our everyday lives because they can swiftly communicate data and trends. They're used in a wide variety of fields, including sales and marketing, science, psychology, economics, and business. Additionally, line graphs can be used to make predictions. Let's look once more at our line graph showing the company's change in profits. Based on the general trend shown, do you think the profits will increase or decrease in the future? We can infer that the profits may continue to increase based on the positive trend shown in previous years. Let's look at another line graph together. This graph shows how much time Dave spent playing video games each day. The horizontal x-axis shows the independent variable, which is days, and the vertical y-axis shows the dependent variable, which is minutes spent playing games. Each marker shows the data point for how many minutes of video games Dave plays each day. Let's use this information to answer some questions. Which day did Dave spend the most time playing video games? Dave spent the most time playing video games on day 4. We know this because the marker for day 4 is higher than the markers for the rest of the days shown. On day 4, Dave played games for 100 minutes. That's a lot of gaming. What is the difference in the amount of time Dave spent playing video games on day 2 and day 6? Looking at the markers, the graph shows that Dave played games for 70 minutes on day 2 and 90 minutes on day 6. The difference is calculated by subtracting. Since 90 minus 70 equals 20, the difference is 20 minutes. Dave spent 20 more minutes playing video games on day 6. How many minutes did Dave play video games altogether? To find the total amount of time Dave played video games, add the amount of minutes played each day. 30 plus 70 plus 60 plus 100 plus 10 plus 90 equals 360. Therefore, Dave spent 360 minutes playing games from day 1 through day 6. A line graph can show multiple sets of data if the same two variables are related. Graphing multiple data sets on a line graph can be very informative because they can be compared and contrasted. When this happens, each data set is typically represented by a distinct color. The line graph contains a key that explains what data set each color stands for. Let's take a look at a line graph that shows two sets of data. This graph shows how much money was raised in a school fundraiser each month. The horizontal x-axis shows the independent variable, which is month, and the vertical y-axis shows the dependent variable, which is amount raised. Each marker shows the data point for how much money was raised in each month shown. The two data sets are graphed in two different colors, blue and green. By reading the key beneath the graph, we see that green represents money raised by 7th grade students, and blue represents money raised by 8th grade students. Let's use this information to answer some questions. Pause the video after each question is asked. Then look at the graph and see if you can answer it yourself. When you're ready, resume and check your work. Which grade raised more money in September? 8th grade students raised more money than 7th grade students in September. Remember that blue data points represent 8th grade students and green data points represent 7th grade students. Looking at the markers for September, we see that the blue marker is higher than the green marker, so 8th grade students raised more money in September. Which grade raised more money in the months of June and August combined? The 8th grade students, shown in blue, raised $60 in June and $60 in August. 60 plus 60 equals 120, so the 8th grade students raised $120 in June and August. The 7th grade students, shown in green, raised $20 in June and $100 in August. 20 plus 100 equals 120. So the 7th grade students raised $120 in June and August. As you can see, both grades raised the same amount of money in the months of June and August combined. In which month did 8th grade students raise the smallest amount of money? How much money was raised? We can find the answer by examining the blue markers representing the 8th grade data points in each month. The month that the marker is placed the lowest is in May, when they raised $40. I have one last graph for you to analyze. This one is a little more challenging, but I know you can handle it. As you can see, this line graph displays 3 sets of data. Consider the following questions. Which variable is independent? Which is dependent? Explain. In which month was the number of computers sold in shop C almost identical to the number sold in shop B? In which months did shop A sell more computers than shops B or C? Pause this video and analyze the line graph, and see if you can answer these questions yourself. When you're ready, resume the video and we'll go over the answers together. Now that you've tried these problems yourself, let's go over them together. Which variable is independent? Which is dependent? Explain. The independent variable is months, which is on the x-axis. The independent variable is always measured along the x-axis, and it usually pertains to time. In this case, time is measured in months. The dependent variable is number of computers sold, which is on the y-axis. The value of the dependent variable relies on the independent variable. In this case, the number of computers each store sold depends on the month. In which month was the number of computers sold in shop C almost identical to the number sold in shop B? March. When we look at the markers for that month, we see that the red marker for shop B and the green marker for shop C almost overlap entirely. This indicates that the number of computers sold by each shop was about the same. In which months did shop A sell more computers than shops B or C? February and March. To find out when shop A sold the most, look for when the blue markers are higher than the green or red markers. Shop A sold 40 computers in February and 50 computers in March. Line graphs are useful tools for showing how factors change over time. Hi, and welcome to this overview of quadratic equations. Before we dive into how to solve them, let's first talk about quadratic functions. When we graph quadratic functions, we'll notice that they can be used to tell all kinds of visual stories, from a daredevil shooting out of a cannon to a satellite dish listening to interstellar signals. Equations for these functions generally look like this. F of x, or sometimes y, equals ax squared plus bx plus c. And their graphs form a characteristic shape called a parabola, which looks something like this one. The different characteristics of quadratic functions that are most commonly analyzed are the vertex, which is the maximum or minimum value, the x-intercepts, which are also known as the zeros, and the axis of symmetry. Now that we have a little background, let's dive further into solving quadratic equations and interpreting the results. So what do we mean by solving? In this case, one of the things it means is to figure out which values of the variable, if any, make the equation 0. So instead of the function f of x equals ax squared plus bx plus c, we write the related equation. 0 equals ax squared plus bx plus c. In other words, the solutions to a quadratic equation are the values that make the quadratic function true when f of x, or y, is equal to 0. This is the function f of x equals negative x squared plus 2x plus 8. Every point on the graph satisfies this equation. Solving 0 equals negative x squared plus 2x plus 8 gives us two solutions, because the function equals 0 only when it crosses the x-axis. Here's another way to look at it. To solve a quadratic equation means to find the x-intercepts of the related function, also known as the zeros. Before you get started with any solving method, make sure your equation is written in standard form. Ax squared plus bx plus c equals 0. This will prevent errors and can provide insight into choosing the most appropriate method for solving an equation. If your equation is not in standard form, simply add or subtract terms as needed. For instance, 2x plus 8 equals x squared is not written in standard form, but by subtracting x squared from both sides, we get negative x squared plus 2x plus 8 equals 0, which is now in standard form. The first method we'll look at is graphing. If you have access to a graph or can easily create one using the internet or a graphing calculator, this can be a great method to use. Let's look at an example. Here is the graph of f of x equals negative x squared plus 2x plus 8. The solutions to the equation negative x squared plus 2x plus 8 equals 0 are x equals negative 2 and x equals 4. Solutions can always be verified by plugging them back into the original equation. Sometimes, quadratic equations can be simplified and solved by factoring. Looking at our sample equation, we have negative x squared plus 2x plus 8 equals 0. The left side can be factored into negative x plus 4 times x plus 2 equals 0. Now let's pause. There's a property called the zero product property that says that if there are two numbers whose product is 0, one of the numbers must be 0. In more mathematical terms, if a and b are real numbers and a times b equals 0, then a equals 0 or b equals 0. Makes sense, right? Back to our equation. Negative x plus 4 times x plus 2 equals 0 means that negative x plus 4 equals 0 or x plus 2 equals 0. So we solve both. We're going to subtract 4 from both sides, which gives us negative x equals negative 4, and then divide by negative 1. We get x equals 4. For this equation, we subtract 2 from both sides, and we're left with x equals negative 2. So our zeros are x equals 4 and x equals negative 2. These match what we found on our graph. Factoring is nice, but not every equation can be factored easily. Luckily, there are a couple more methods we can use, including the completing the square method. The idea behind this method is to create a quadratic equation that contains a perfect square, and then take the square root to find the solutions. Here's our equation again. Negative x squared plus 2x plus 8 equals 0. To complete the square, the equation needs to not only be in standard form, but the coefficient on the squared term needs to be positive instead of negative. So we divide all terms by negative 1 to get ready. This gives us x squared minus 2x minus 8 equals 0. First, move the constant term to the other side by itself. For this, we'll add 8 to both sides. This gives us x squared minus 2x equals 8. Pause. Now we need to add a number that creates a perfect square on the left-hand side. Let's consider some perfect squares. To complete the square in our equation, we'll need to add a number to both sides of our equation. In the examples, notice that the number is b over 2 squared. 4 equals 4 over 2 squared, 9 equals negative 6 over 2 squared, and 16 equals 8 over 2 squared. In our equation, we'll add negative 2 over 2 squared, which equals 1, since our b is equal to negative 2. Remember, an equation only stays equal if you change both sides in the same way. So since we're going to add 1 to our left side, we also need to be sure to add 1 to the right side. Now the left side can be factored. X minus 1 squared is equal to 9. Since we have a perfect square, we take the square root of both sides. On the right-hand side, we need to account for both positive and negative square roots. Now we'll split into separate mini-equations. X minus 1 equals 3, and x minus 1 equals negative 3. We're going to solve for x over here by adding 1 to both sides, which gives us x equals 4. And here we're going to do the same, add 1 to both sides, which gives us x equals negative 2. We get the same solutions as before. Completing the square can be used with any quadratic equation, but if you start with a perfect square and don't realize it, the equation will look the same after you use this method as it did when you started. There is one last method for us to examine. The quadratic formula, as you'll see, involves the most algebra, but it has two distinct characteristics. One, it can truly be used with any quadratic equation, and two, part of it can be used to determine how many solutions to expect beforehand. Here it is in all its glory. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. The piece of the quadratic formula under the radical, the square root sign, is called the discriminant. Calculating its value helps us know how many solutions to expect. Let's take a minute to consider how many times a quadratic function can possibly intersect the x-axis. This example shows twice. Sometimes it's only the vertex, and sometimes not at all. Because of the shape, these are our only choices. In order for a graph like this to intersect the x-axis more than 2 times, it would need to change direction again and thus no longer be a parabola. Now let's consider square roots in general. If the square root of a number is greater than 0, there are 2 real solutions. Taking the square root of a positive number yields positive and negative roots. If the square root is 0, there is one real solution, 0. Taking the square root of 0 is 0. If the square root of a number is less than 0, there are 0 real solutions. We can't take the square root of a negative number and end up with a real number. So what does this have to do with the discriminant? If b squared minus 4ac is greater than 0, then there are 2 real solutions, 2 x-intercepts. If b squared minus 4ac equals 0, there is one real solution. The vertex of the parabola is the x-intercept. And if b squared minus 4ac is less than 0, there are no real solutions, no x-intercepts. Using our ongoing example, negative x squared plus 2x plus 8 equals 0, a equals negative 1, b equals 2, and c equals 8. The discriminant d is b squared minus 4ac, which is 2 squared, minus 4 times negative 1 times 8, which is equal to 4 plus 32, which is equal to 36. Since 36 is greater than 0, we know that there are 2 real solutions to our equation, as expected. What's the point of calculating the discriminant? If you get in the habit of checking it every time, a few things happen. If there are no solutions to your equation, you'll know right away and can stop. If there are 1 or 2 solutions, the discriminant will serve as a check, regardless of the method used. If you use the quadratic formula, a chunk of it is already calculated. Speaking of the quadratic formula, let's try it out. Again, a is equal to negative 1, b is equal to 2, and c is equal to 8. Plus, we already know the discriminant. So we have negative b, which is negative 2, plus or minus the square root of the discriminant, which we found was 36, so the square root of 36, all over 2 times our a, which is negative 1. This is equal to negative 2 plus or minus 6 over negative 2. Now we're going to split it into 2 equations. We have negative 2 plus or 6 over negative 2, and negative 2 minus 6 over negative 2. This one is equal to 4 over negative 2, which is negative 2. This one gives us negative 8 over negative 2, which is equal to 4. So x equals negative 2 and x equals 4. We've seen all 4 quadratic equation solving methods in action. Now let's put some context around our practice equation. Suppose our function f of x equals negative x squared plus 2x plus 8 represents the height of a rock from the ground in meters you throw off of a small cliff as a function of time in seconds. We want to know how long it takes for the rock to hit the ground. In order to do that, we would solve the equation negative x squared plus 2x plus 8 equals 0, which we have already done many times over. Remember, the 0 represents 0 height. In function terms, this means on the x-axis. In this situation, that means on the ground. We know that our mathematical solutions are x equals negative 2 and x equals 4. In this situation, the solution of negative 2 doesn't make sense. What does it mean? 2 seconds ago? Travel back in time 2 seconds? We would state that the rock landed after 4 seconds. Hello, and welcome to this video about using the quadratic formula. Today we'll learn what the quadratic formula is, when you use it, and how it's applied to find roots in quadratic equations. Let's start by talking about quadratic equations. A quadratic equation in standard form is written as ax squared plus bx plus c equals 0, where a doesn't equal 0 and a, b, and c are all real numbers. The quadratic formula is an algebraic equation that helps solve any quadratic equation. The formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. By substituting in given values for the variables a, b, and c, you can solve for x using the quadratic formula. Solving for x gives us solutions for the quadratic equation. These solutions are also called roots. Let's consider the quadratic equation x squared plus x minus 6 equals 0, and use the quadratic formula to find solutions for x. First, identify the values for the variables a, b, and c in the quadratic equation. Since the first term, x squared, is the same as 1x squared, the value for a is equal to 1. In the second term, x, the value for b is also equal to the coefficient of 1. And since the last term is negative 6 or minus 6, the value for c is equal to negative 6. Next, substitute the values for a, b, and c into the quadratic formula. So let's write out our quadratic formula again so that we remember it. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And now we're going to plug in our a, b, and c into this equation. So x is equal to negative 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 6 all over 2 times 1. From here, solve for x using the quadratic formula. So all we have to do is simplify. So we're going to leave the negative 1 right here for now and move on to this part. So we have the square root of 1 squared is 1 minus 4 times 1 times negative 6 is negative 24. So minus negative 24 over 2 times 1 is 2. 1 minus negative 24 is the same as saying 1 plus 24, which is 25. The square root of 25 is 5, so we have negative 1 plus or minus 5 over 2. And now we're going to break this part into two different equations. So we're going to have negative 1 plus 5 over 2. Remember, x is equal to this, so this is one of our values for x. So negative 1 plus 5 is 4, over 2 is 2. And then for our other value of x, we're going to do x is equal to negative 1 minus 5 over 2. Negative 1 minus 5 is negative 6, over 2 is negative 3. So the roots for this quadratic equation are 2 and negative 3. In the example we just looked at, there were two possible solutions or roots for x. Quadratic functions can have two solutions, one solution, or no real solutions for x. To figure out how many solutions a quadratic equation has, look at the discriminant in the quadratic formula. The discriminant is the portion of the quadratic formula that's beneath the square root symbol. It's the part that's read as b squared minus 4ac. When simplified, the discriminant can be a positive number, a negative number, or 0. And its sign tells us how many solutions the quadratic equation has. When the discriminant is positive, then the quadratic equation has two real solutions. When it's negative, then it has no real solutions. And when the discriminant is 0, then the quadratic equation has exactly one real solution. In the previous example, the discriminant was 25. Since it's a positive number, we know that the quadratic equation has two real solutions, which is what we found when we worked it out. Let's look at another example. Consider the quadratic equation 10x squared minus 9x plus 6 equals 0. And let's use the quadratic formula to find the solutions for x. First, we need to identify the values for the variables a, b, and c in the quadratic equation. Our first term, 10x squared, tells us that a is equal to 10. Our second term, negative 9x, tells us that the value of b is negative 9. And our third term, plus 6, tells us that c is equal to 6. Now we're going to use the quadratic equation to solve this problem. So our formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now remember, writing out formulas helps you remember it, so whenever you can, it's a really helpful thing to do. Now all we have to do is plug in our numbers for our variables. So negative b is negative 9, so be careful when plugging it in. You need to make sure you have the negative 9. Plus or minus the square root of b squared is negative 9 squared minus 4 times a is 10 times c is 6 all over 2 times 10, which is equal to minus a negative is equal to a positive. So we're going to have positive 9 right here, plus or minus the square root of negative 9 squared is 81. And then 4 times 10 times 6 is 240. So we have minus 240 all over 2 times 10 is 20. So this gives us 9 plus or minus negative 159 over 20. And we can stop right here because we see our discriminant is negative 159. Negative numbers don't have real square roots because a square is either positive or 0. So remember, if the discriminant is negative number, then there are no real solutions to the equation. So we can stop right here. Our answer is that there is no real solutions for x. Now it's your turn. I'm going to give you a quadratic equation, and you need to use the quadratic formula to identify the possible roots for x. 9x squared plus 12x plus 4 equals 0. Pause the video here and try it yourself. And when you're done, resume the video and we'll go over everything together. Let's take a look at this one together. Start by identifying the values for a, b, and c. Based on the equation, we can see that a is equal to 9, b is equal to 12, and c is equal to 4. Next, substitute the values for a, b, and c into the quadratic formula. So remember, the formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then we just take our numbers up here and plug them in for all our variables. So we have negative 12 plus or minus the square root of 12 squared minus 4 times 9 times 4 all over 2 times 9. So this simplifies to negative 12 plus or minus the square root of 12 squared is 144 minus 4 times 9 is 36 times 4 is 144 all over 2 times 9 is 18. So then we have negative 12 plus or minus the square root of 0 over 18. The square root of 0 is 0, so all we have is negative 12 plus or minus 0 over 18. And if you add or subtract 0, that's not going to change your number at all, so this is really the same as negative 12 over 18, which we can then simplify by dividing both the numerator and denominator by 3. So that'll give us negative 4 over 6. And we can simplify that one more time by dividing both by 2 to get negative 2/3. So x is equal to negative 2/3. And that's our root for this equation. Quadratic functions occur in many real-world situations. One example is shooting a cannonball out of a cannon. When you do this, it goes up and then it comes back down in the shape of a parabola. Since a parabola is the graph of a quadratic function, you can use the equation for the path the cannonball follows to answer questions about its time, speed, and distance. There are lots of other problem-solving instances in which quadratic equations are helpful. Understanding them helps us apply mathematical concepts in the real world. I have one more problem for you to try. Let's take a look at a word problem that we can solve by using the quadratic formula. A high school physics club shoots a model rocket into the air from 12 feet above the ground. The initial velocity of the rocket is 19 feet per second. The equation h equals negative 10x squared plus 19x plus 12 can be used to show the height of the rocket after x seconds. How long does it take for the rocket to hit the ground? We can solve this problem by applying the quadratic formula to the equation given in the scenario. This problem is a little bit more challenging, but I know you can handle it. Pause the video here and try it yourself, and when you're done, we'll go over it together. Let's take a look at this one. In this scenario, we are looking for the amount of time it takes for the rocket to reach the ground. The height, h, at ground level is 0 feet. Therefore, we can replace 0 for h in the equation. So we can rewrite it as 0 equals negative 10x squared plus 19x plus 12. And now it looks like our quadratic equation in standard form, just with our 0 on the left side instead of the right side. So now that we understand that our equation is really just in standard form, we can identify the values for a, b, and c. Based on our equation, we see that a is equal to negative 10, b is equal to 19, and c is equal to 12. Now we can substitute these values into our quadratic formula. So we have the formula again is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now we can plug in our numbers. So we have x is equal to negative b, so negative 19, plus or minus the square root of 19 squared minus 4 times negative 10 times 12 all over 2 times negative 10. So this is equal to negative 19 plus or minus the square root of 19 squared is 361 minus 4 times negative 10 times 12 is negative 480 over 2 times negative 10 is negative 20. So this is equal to negative 19 plus or minus the square root of 361 minus negative 480 is the same as saying plus 480. So the square root of 841, that's what you get when you add those two numbers together, over negative 20. So this is equal to negative 19 plus or minus the square root of 841 is 29 over negative 20. And now from this step, we're going to take this equation and break it into two separate equations because of this plus or minus. So we're going to have x is equal to negative 19 plus 29 over negative 20. And we're also going to have x is equal to negative 19 minus 29 over negative 20. Negative 19 plus 29 is equal to 10 over negative 20. Simplifies to negative 1/2. And over here, negative 19 minus 29 is negative 48 over negative 20. Our negatives will cancel each other out. And if we divide both the numerator and denominator by 4, we'll get 12 over 5. So the solutions to this equation are x equals negative 1/2 and x equals 12 over 5. Now that we have the two roots for x, we must interpret what they mean in the context of the word problem. Recall that x stands for seconds, measuring the amount of time it takes for the model rocket to hit the ground. Time is measured with positive numbers, not negative numbers. Therefore, the negative root of x does not apply to this scenario. Based on the positive solution for x, the amount of time that it will take for the rocket to hit the ground is 12 over 5 seconds. Great work! Hello, and welcome to this video on domain and range. In this video, we will see what domain and range are and how to find the domain and range of a function. Remember, a function is a relation between two sets of numbers, an input and an output. Each element of the input produces a unique element of the output. The domain of a function is the set of all possible inputs of a function. This means that it is any number you can plug into a function. For most functions, this will be any number you can plug in for the letter x. Almost every time, your domain will be all real numbers, except for a special few cases like square root functions and rational numbers. The range of a function is the set of all possible outputs of a function. Typically, this will be represented by the letter y or f of x. The range is any number that you can get when you plug in any number for x. Let's look at a simple linear function, y equals 4x plus 3. We're going to find the domain and range using just the equation by looking at a graph and by looking at a table. Let's think about this algebraically for a minute. The domain is any number we can put in place of the x. You could put 1, 2, -7, 84, or any other number in place of the x. This means that the domain is negative infinity is less than or equal to x is less than or equal to positive infinity. Another way to say this is that the domain is the set of all real numbers. What about our range? Well, if I plug in 1 for x, I get 7, and if I plug in 2 for x, I get 11. But I can also plug in 1.5 for x, which would give me 9, or 1.25 for x, which would give me 8. I can plug in any decimal number, so for this equation, I can also get out any number for y by searching for the right x. The range of this function is also the set of all real numbers. Now I want to check this graphically. If we graph this function, we see that it is a line. Lines continue across every value of x and every value of y. This matches up with what we found out by thinking through it algebraically. This further proves that the domain and range are both the set of all real numbers. Now let's look at a table of values for the first 4 terms of this function. In this case, we are only looking at a portion of the function, so our domain of values would be 1, 2, 3, and 4. And our range of values would be 7, 11, 15, and 19. Let's try a couple of examples. What is the domain and range of the function y equals x squared minus 4x plus 3? The domain is the list of numbers that can be plugged in for x. You can plug in any number for x, so the domain is the set of all real numbers. What about our range? Let's figure this out by looking at a graph of the equation. Remember, our range is every possible value for y. If we look at our graph, we see that it is a parabola that opens up with a vertex at 2, -7. This means that our range is y is greater than or equal to -7. Let's try one more example, this time using a table for the function y equals 2x minus 1. What would be our domain and range given this table? Our domain would be 7, 14, 21, and 28, and our range would be 13, 27, 41, and 55. If we wanted the domain and range for the whole function, we would consider what numbers we can plug in for x and what corresponding y values we would get. Well, we can plug in any number for x, and it is a linear function, so we can get any number for y. Therefore, the domain and range of this function is all real numbers. Remember, if you are finding the domain and range of a function algebraically, think about what numbers you can plug in for x and the resulting numbers you will get for y. If you are finding the domain and range given a graph, follow your finger along the graph to see what x values it covers and what y values it covers. Finally, if you are looking at a table, the domain is the list of numbers inputted for x, and the range is the list of numbers that are the outputs of those x inputs, the numbers in the y column. Hi, and welcome to this video on common functions. Let's start by reviewing the formal definition of a mathematical function. As you may remember, a function is a special type of relation. In math, we use relations to manipulate input to result in a specific output. The input of a relation is referred to as the domain and is comprised of the x values of an ordered pair. The output of a relation is called the range and is the y value of an ordered pair. A relation is characterized as a function if every element of the domain produces exactly one result that is in the range. For example, if x equals 2 is substituted into the function and results in y equals 8, then that is the only range value that can be associated with x equals 2. Some relations that classify as functions map several x values to the same y value. If x equals -2 is substituted into the same function and also results in y equals 8, that is acceptable. Several domain values can map to the same range value. However, there's a special type of function that maps each domain value to a unique range value. These functions are referred to as one-to-one. Now that we have the definition of a function in mind, we can discuss how functions are classified. Algebraic functions are mathematical expressions that involve the operations of addition, subtraction, multiplication, and division. Also falling into this category are expressions that have powers and involve roots, which are known as radical expressions, and expressions that are rational, which can be seen as fractions. Functions that do not fit these descriptions are said to be transcendental functions. These types of functions include trigonometric, exponential, and logarithmic functions. There are many different types of algebraic functions. The first type we're going to look at is the polynomial function. Polynomial functions cover a broad category within the classification of algebraic functions. Polynomial functions are defined as having powers of one or more variables. This means that the variables can be raised to whole number exponents, but cannot be negative or decimals. Terms of a polynomial are joined by the operations of addition or subtraction. Polynomials can have one or more terms, and polynomials are often named according to the number of terms. The degree, or the highest exponent of the polynomial, is also used as a distinguishing feature in the function. It is important to note that a constant can be viewed as a monomial with a variable raised to the power of 0. If any number or expression raised to a power of 0 is equivalent to 1, then it follows that the term 5 times x to the 0 simplifies to 5 times 1 equals 5. Here's a list of polynomials named by degree. Linear functions are polynomials of degree 1. The structure of a linear equation is y equals mx plus b, where m and b are constants representing the slope and the y-intercept of the line respectively. Function notation f of x is typically used rather than y when evaluating a function. For example, if f of x equals 2x plus 3, then f of -1 equals 2 times -1 plus 3, for a value of f of -1 equals 1. If we evaluate this linear function at other values of x around the origin, we see that the graph results in a straight line. The orientation of the line depends on the constants m and b. A constant function is a particular type of linear function that results when m equals 0 and b is any constant. Using the linear function f of x equals 0 times x plus 5, we quickly see that no matter what value of x is substituted into the function, our y value will be a constant, in this case equal to 5. The graph of a constant function, therefore, will be a horizontal line at y equals 5 for all values of x. The identity function is a linear function where m equals 1 and b equals 0. Consider the effect on the linear function f of x equals 1x plus 0, which simplifies to f of x equals x. This means that for any value of x that is substituted into the identity function, the y value is equivalent to the input x. Now that we have discussed linear functions and how they graph straight lines, we can move on to quadratic functions and the parabolas that they graph. The quadratic function can be recognized in standard form as f of x equals ax squared plus bx plus c, where a, b, and c are constants. The squared variable of the quadratic ensures symmetry in the parabolic shape that is graphed, meaning that each point on the graph, with the exception of the vertex, will have a mirror image on the other side of the graph. The parent function of a quadratic function is y equals x squared, which has a leading coefficient of a equals 1. The coefficient of the linear term and constant are both 0. The vertex of the parent quadratic function is at the ordered pair 0, 0. Changing values of a, b, and c result in transformations of this parent function. Transformations include changes to shape, the direction of the parabola opening, and the location of the vertex. As mentioned previously, polynomials are one type of algebraic function. Understanding the polynomial structure is important in the study of rational functions, which are defined as a fraction of two polynomial expressions. It is very important to take a careful look at the denominator of a rational function, because it is mathematically impossible to divide by 0. When working with rationals, be sure to identify the x values that would result in a 0 as the denominator. Those values must be excluded from the domain of the function. For example, consider the rational function f of x equals x squared plus 5 over x plus 2. If this function were to be evaluated at x equals negative 2, we would have an undefined result as shown. Note that the graph does not exist at the value x equals negative 2. These points of discontinuity in a rational function are referred to as vertical asymptotes. The branches of the graph will approach but never touch the excluded values of the domain. The square root function is a specific type of radical function. The image provides the important parts of a radical expression. The index is the value indicated as n in the radical symbol. The radicand, in this case x, can be a constant, variable, or expression that is under the radical symbol. The parent square root function is written as f of x equals the square root of x. As you can see, there is no index notated in the square root function. When there is no index, you should assume that the n equals 2, and you will determine the square root of the radicand. Ask yourself, what can I multiply by itself to get the radicand? As you can see in the table in the graph, the square root function has x values restricted from the domain, namely all negative integers, because it is not possible to arrive at a negative value or radicand by multiplying a number by itself. Now we can move on to the other classifications of functions, known as transcendental functions, which are not algebraic in nature. Trigonometric functions are widely used in geometric applications. Distances and other measurements needed for engineering, surveying, and physics are found by using trigonometric properties. The three basic trigonometric functions of sine, cosine, and tangent are actual side length ratios determined by either of the acute angles in a right triangle. Reciprocal functions for sine, cosine, and tangent are cosecant, secant, and cotangent respectively. The graph for the sine function resembles a continuous, repeating wave with a range of values between -1 and 1. Exponential functions are unique in structure because the variable is in the exponent position of the function. The function y equals 2 to the x has a base of 2 raised to the power of x. Exponential growth is the result of raising a base that is greater than 1 to an exponent that is increasing in value. If a fraction between 0 and 1 is raised to an exponent that is increasing in value, the result would be a rapidly decreasing pattern, or exponential decay. Exponential functions are used frequently in science and business applications. A logarithmic function, or log function, is the inverse of an exponential function. The graph of a log function is the reflection of an exponential function about the line y equals x, the identity function. Let's take a closer look at the parts of an exponential function and a log function so the inverse relationship can be understood better. As stated previously, y equals 2 to the x has a base equals 2 and an exponent of x. This exponential equation can be converted to a logarithmic function as follows. X equals log base 2 times y. A log function names the base of the function as a subscript of the log, in this case 2. The y of the log function is called the argument, and the solution to a log function is the power of the exponential function. It is often helpful to ask yourself, what power would I have to raise the base to in order to get the argument? Let's use actual numbers to illustrate this question. A base of 2 would have to be raised to the power of 3 to get a value of 8. Logs return the power. The two most common types of log functions have a base 10, called a common log, and a base e, called a natural log, notated as ln. Note that e is not a variable but an irrational number, like pi, with an approximate value of 2.718. If no subscript is indicated on a log, assume that it is a common log with a base of 10. Log functions provide a shorthand way of dealing with large numbers. Working with the exponent on a base of 10 is easier to manage than the very large argument. A great example is the Richter scale, which measures the magnitude of earthquakes. For example, an earthquake measuring 7.1 on the Richter scale would translate to the exponential equation 10 to the 7.1 power equals 12,589,254 microns, or the log of 12,589,254 equals 7.1. There are a few common characteristics of all functions that can be recognized. A monotone function is always increasing as x values increase. This means that the change in y values is always positive as x values increase. Conversely, the y values of the function can always be decreasing as the x values increase. The change in y values would be negative in a decreasing function. Functions can also be characterized as even, odd, or neither. Even functions have vertical symmetry about the y-axis. In order to test whether a function is even, the following equation must be satisfied. F of negative x equals f of x. For example, suppose you have a quadratic function f of x equals x squared plus 1. To test whether this function is even, simply substitute a negative x value and determine whether it is equal to the function evaluated at the positive x value, as follows. F of negative x equals negative x squared plus 1, which is equal to x squared plus 1, which is equivalent to f of x. This function is even. Another special type of function that can be classified as even is called the absolute value function. This type of function actually measures the distance of the expression inside the absolute value bars from 0. Accordingly, the absolute value function always returns a positive result because distance cannot take on a negative value. Unlike the smooth curve of a parabola, the absolute value function can be viewed as the intersection of two straight lines. The right side measures the distance of positive integers from 0, and the left side measures the distance of negative integers from 0. Here's an example of the parent absolute value function, which clearly has symmetry about the y-axis, and would therefore be considered even. The trigonometric function f of x equals cosine x is also even, due to its symmetry about the y-axis. Functions that are considered odd would satisfy this equation. F of negative x equals negative f of x. Odd functions have symmetry about the origin. The cubic polynomial function f of x equals x cubed minus x is classified as odd because substituting negative x into the function results in the following. F of negative x equals negative x cubed minus negative x, which is the same as negative x cubed plus x. Factoring out negative 1 from each term results in negative x cubed minus x, which is equivalent to negative f of x. A quick look at the graph of the trigonometric function f of x equals sine x shows symmetry about the origin, indicating that it is also odd. As mentioned, a function can be neither even nor odd if the above equations and symmetric properties are not satisfied. The graph here clearly does not have symmetry about the y-axis nor about the origin. This overview is not exhaustive of all functions that you will see in your math courses, but it does touch on the major classifications, characteristics, and terminology that you will encounter. Thanks for watching and happy studying.